EET 105, example 1026 capacitors. For the network in figure 10.98, part A, write the mathematical expressions for the voltages VC and VR1 and the current IC after the switch is thrown into position 1. So that would be a charging situation. So the first thing you do is calculate tau. Tau is R times C. When you throw it into 1, again, the total R is this R plus this R, because this is going to be one loop right here. So it's 3K plus 2K times 2 microfarads equals 10 milliseconds. So the equation would be, the charging equation would be 30 volts, which is a source voltage, times 1 minus e to the minus t over 10 milliseconds, which is tau. Then IC would be 30 volts divided by 5K. We're still in charging mode, so this is the equation for it. E to the minus t over 10 milliseconds. That equals 6 milliamps. And that should be times e to the minus t divided by 10 milliseconds. They forgot the e in here. So that's what that 30 divided by 5K is, 6 milliamps. VR1 equals IC times R1, which is 6 milliamps times 3 kiloohms times e to the minus t over 10 milliseconds equals 18 volts times e to the minus 10 e to the minus t divided by 10 milliseconds. Now in part B, it says find values of VC, VR1, and IC when the switch is moved to position 2 at t equals 100 milliseconds. Well, at 100 milliseconds, that's 10 times tau. So at that point, the capacitor is fully charged. We're moving it to position 2. So they put e to the minus 10, which is tau equal to 10t divided by tau, ends up equaling minus 10. It would be minus 10 tau over tau, which is minus 10, or just minus 100 milliseconds divided by 10 milliseconds equals to the minus 10 equals that. And then V sub C equals 30 volts because the capacitor is fully charged times 1 minus e to the minus 10 equals 30 volts. Okay, because this number is basically 0. It's a very, very small number. I sub C again would be the 6 milliamp times e to the minus 10, which is 0.27 microamps, very, very small. And then VR1, which is over here, is 18 volts times e to the minus 10. And the reason why it's 18 volts is because we figured it out right here where this is VR1. So it's 0.82 millivolts. Part C, write a mathematical expressions for the voltages VC, VR2, and the current IT, IC if the switch is moved to position 3 at 2 equals 200 milliseconds. So again, when it's moved to position 3, now you have this loop, okay, and the current's actually going the opposite way as IC is shown here, and it's discharging. So you have to, they called it tau prime, which would be a different tau because now R2 is the only resistor involved. R1's no longer involved, so it's R2 times C, which ends up equal to 4 milliseconds. Then VC, using the discharging equation, equals 30 times e to the minus t over 4 milliseconds. And then again, IC is negative only because it's shown the wrong way here, so it's actually going the other way. 30 volt divided by 2K, which is R in this circuit, times e to the minus t over 4 milliseconds equals negative 15 milliamps times e to the minus t over 4 milliseconds. At t equals 0, VR2 equals ICR2 equals that equation, and the t equals 200, VR2 equals minus 15 milliamps times 2 kiloohms times that equation. So they're using the initial tau for the initial equation here, and then for the final equation they're using E equals E over R, which is that 30 divided by 2K. It's this number here, 15 milliamps. The 6 milliamps came from here when it was charging up. So they're just showing you the difference of the two voltages. And then D, it says plot the waveforms of VC, VR2, and IC for the time period extending from 0 to 300 milliseconds. Well, VC starts at 0 and then it charges up. After 5 tau is 50 milliseconds, and then it just continues to basically plateau at 30 volts at 100 milliseconds, and at 200 milliseconds, when we said that we moved the switch, it's going to discharge to 0. Okay, and it's just going to stay at 0. IC starts off at 6 milliamps, and then it discharges down, or I mean the current starts off at 6 milliamps and it decays down to 0. Basically after 5 tau equal 50 milliseconds it stays at 0, and then it jumps negative to minus 15. That's this right here, and then it decays back down to 0 after 5 tau, which is 20 milliseconds, which would be 5 times this 4 milliseconds here. And then VR2 starts off at 12 volts, as shown here, and it decays down to 0 after 5 tau, goes to 0, and then at t equals 200 milliseconds, it jumps down to negative 30 volts, and then it decays down to 0 after 5 tau, which is 20 milliseconds, just like the current did. It follows the current, basically. It looks the same as the current, but it's on a different scale.